Uh, so last week we learned a bit about single qubit gates, and we touched just for a few seconds, I guess, uh, about two qubit gates, right? And today we will learn more about that. And to get started, or this is a bit of a revision from last week. So what did we learn last week? Last week we learned about different kinds of single qubit gates, right? Gates that you operate on single qubit. Qubit has two levels, 0 and 1, and um, 0 is what we call ground state, and 1 is what we call excited state. And you can write that in vector notation as something like this, right? Sorry, this is getting a little bit messy, but just please bear with me. And you can write state 1 as something like this, right? 0, 1. So that forms what we called your computational system, right? And we call it computational because that is where you encode your data for your computer, or quantum computer rather, to process, right? So you can encode, for example, your name. Let's say Laxman, right? Laxman, that's a string. You can encode it in a bunch of these zeros and ones, right? 0, 1, 1, 0, 0, right? So these are your computational states that define what you store on it. And the idea of this computational states is very important, because when you're performing operations on this qubits, you always want to stay always want to act on computational states, right? Although, for example, for practical implementation, we also use non-computational state, but this is the most fundamental, right? So ideally, we want two isolated states, 0 and 1. And now matrices, right, or single qubit operations that act on computational states, or single qubit, are Pauli X gates, right? So that is a fundamental single qubit gate, Pauli Y gate, and Pauli Z gate, right? So they rotate your state vector around different axes of this block sphere, if you remember from last time. So block sphere is a geometric representation of a single qubit state, and points on the surface of block sphere define arbitrary combination of these zeros and ones, right? And so if you have X gate, what it does, it X gate acts on, for example, 1, 0 state and gives you 0, 1 state. If you act with X gate on 0, 1 state, right, it gives you 1, 0, right? So it is very simple. And you have other gates, Hadamard gate, which you use to form superposition. So you see, if you use Hadamard gate and act on this 1, 0 state, which is the first state of qubit, it gives you superposition, right? It gives you something like this. This is the result of acting Hadamard gate on first state, which is 0 state of your qubit. It's going to give you superposition of 0 here, superposition of 1 state, right? And these are almost trivial gate. They just add a phase of, for example, pi/4 on your qubit, right? So it's very, very simple. Mathematically, it's nothing else than just some matrix multiplication. And this will be the outcome of performing the single qubit gate operations on your qubit states. Do you guys have any question regarding this? All right. Okay. Okay. Now let's go on to I would say a little bit more complicated gate operations, which I call 2-qubit gate. And 2-qubit gates are another building block of quantum computer. So single qubit gate, I hope it is clear, very, very simple. You just act on 2-level system, and 2-qubit gate acts on 4-level system. Why? Because we need 2 qubits, right? So 2 qubits means there are 4 computational states a qubit can be in, or superposition of these computational states, right? So 2 qubits had 2 levels, right? So how do you count the number of computational states? By simple integer multiplication. If you have a qubit with 2 levels, 0 and 1, how many states are there? 2 to the power 1. Right, Rajkumar Dahal says if you have n qubits will give you 2 to the power n different states, right? So that is the whole point. So now for single qubit, you had 2 to the power 1 state, just 0 and 1, right? 1. If you have 2 qubits, n is 2. You have Rajkumar Dahal, sorry. If you have 2 qubits, you have 2 to the power 4 different states. So how do you represent them in this Ket notation? By doing something like this: 0, 0, 0, 1, 1, 0, 1, 1. Right? Very, very simple. So these are your computational states, right? So you can represent your data as a superposition of all these states, for example, right? And this is very handy. With increasing number of qubits, you can store more information in your quantum RAM, right? And for single qubit gates, we perform single qubit operations, right? For 2 qubit gates, we perform 2 qubit operations. And 2 qubit operations are defined by this 4x4 matrix because we have 4 different computational states, or as we call in mathematics, basis states. You need to construct 4x4 matrix and not 2x2 matrix, right? So that is something different from single qubit gate. And 2 of the most fundamental 2 qubit gates are CNOT gate and C-phase gate. And in matrix notation, they look something like that, right? So that is in matrix notation. So these are like Ket notation, right? These were like Ket notation. Paul Dirac, he has written a book which we were learning in our high school, and that book of his was the one that first introduced this Brian kit. So Dirac made some significant contribution in terms of formalizing quantum mechanics, right? So you can write or define your qubit states in terms of this bracket notation. We call them bracket notation, or in terms of this vector notation, right? And now what does 0, 0, 0, 1, 1, 0, 1, 1 look like in vector notation? For that, we can look into our QTip simulation. So let me show it to you. So that is my QTip program, right? So just have a look here. Now, let's first do 0, 0, right? So what does 0, 0 look like in vector notation? So that is 0, 0. You can try that at home with your QTip simulation. So let me run this code. It gives you 1, 0, 0, 0, right? Now, if I have 2, 0, 2, 1, so 0, 0, 1, what does it look like? It looks like 0, 1, 0, 0, right? Now, next one, third one, 1, 0. What does 1, 0 look like? The third element will be 1, obviously. Now the final one, 1, 1, right? What does the 1, 1 state look like? One look like 0, 0, 0, 1, right? So Rajkumar Dakal asks, is it okay if I use Qiskit for learning? It's definitely fine. Qiskit, I will also introduce Qiskit in some time. They have the same underlying structure of quantum mechanics, right? So it's just commands that are different from QTip to Qiskit. Qiskit is from IBM, and they use specifically for simulating quantum systems in IBM's quantum chip. That's their software interface, right? But QTip wasn't designed necessarily for quantum computing. It is in general to do tasks that involves quantum theory, and it is more general than Qiskit, I would say. But you can use either. They will do the same job at the end, right? Because we are simulating quantum systems and trying to perform gate operations, and we call it Hamiltonian evolution, right? Or unitary evolution described by certain Hamiltonian on quantum system. So at the end, you can use either, and you will benefit from using either, I would say. But it's very simple, right? So for us, when we had single qubit, you had two basis states. What were those? 0, 0. Sorry, 1, 0 and 0, 1, right? But now I have two qubits, so we have four basis sets. Why? Because 2 to the power 2. That is how many possibilities you have for qubit to be in, right? So that's just a combination permutation problem, you used to do in high school. It's like 2C1 times 2C1, right? So the first can be either 0, 1 times the second can be either 0, 1, right? So that gives you four different possibilities. So if you had single qubit, again, to repeat, you have states 1, 0, 0, 1. If you have two qubits, you'll have four states: 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, right? So that will be our computational system, right? So now going back to our presentation. So again, we perform similar gate operations with different 2-qubit gates, and our two different 2-qubit gates are CNOT gate and C-phase gate. They're both very fundamental to quantum computation, and this is something you guys have to understand, I would say, by heart, right? So what does CNOT gate do? So if you start your qubit in state 0, 0, CNOT gate does nothing. If you start your qubit in state 0, 1, CNOT gate does nothing. But if you start in the first qubit as 1, second qubit as 0, it changes the state of second qubit to 1, right? If we start first qubit at state 1, second at state 1, it changes the state of second qubit to 0, right? So what is happening here? It is conditionally flipping the state of second qubit, right? So the condition is on the state of first qubit. You are given, so qubit, the first qubit, depending on the state of first qubit, you either change or don't change the state of second qubit, right? So this is exactly what CNOT gate is doing. And C-phase gate works very similarly. So what does it do? If you have input 0, 0, output will be 0, 0, does nothing. If you have input 0, 1, output will be 0, 1, does nothing. If you have input 1, 0, output will still be 1, 0. It does nothing. But if you have input 1, 1, output will add a phase of -1. So this C phase gate is conditioned upon state of both qubit, not just single qubit, but both qubit, right? So it's a symmetric gate. You have to have both qubit to be in 1, 1 state to have a non-trivial output, right? So this is exactly what C phase gate does. And both are very important to qubit gate, and some companies, they implement in their architecture C0 gate. Our company, for example, at IQM, we try to implement C phase gate, right, in our superconducting quantum computing architecture. Sorry. So now again, let's go to the truth table. So C phase right? So what does it look like? It looks like 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, -1, right? So let us check what happens. Now you apply this on 0, 0 state. What was our 0, 0 state? Our 0, 0 state was 1, 0, 0, 0. That gave you the same state, right? 1, 0, 0, 0, right? Now if you apply this on, for example, 0, 1, 0, 0 state, it will give you the same thing. Now if you apply this on 0, 0, 0, 1, so what does it do? You multiply this, it gives you 0. You multiply this row with this column, still 0. This row with this column, 0. And now you multiply this row with the column vector here, it gives you -1, which you can write as -1, 0, 0, 0, 1, right? So this was 1, 1 state. It gave you -1, 1 state, right? And this is something, this really simple operation is something that makes your quantum computer a quantum computer. This is one of the most fundamental 2-qubit quantum operation, which you have to build almost perfectly in lab to build a working quantum computer. And we can do the same thing with C0 gate. Let us try that. All right, so we try that with C0 gate. So C0 gate looks like that, right? So it has 0, 0, here 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, right? 0, 0, 0, 1, right? So, oh, sorry. So it's the other way. Yeah. So it's going to be here. Here, right? Okay. Now, if you act that on, let's say, the first qubit or the first state, first basis state, it will give you the same thing, right? Same. Right now, if you act that on 1 0 state, which will be 1 0 state, what does it give you? Let's do it. This will be 0. This will be 0. This will be 0. This will be 1. So 1 0 state will go to 1 1 state, right? Now what happens if you do it to 1 1 state? Right, so that will be so if you do this to 1 1 state, so it's just again matrix multiplication. It gives you 0 0 1 0, right? So 1 1 state became 1 0 state, right? So it just, depending on the state of first qubit, it flips the state of second qubit. If the second qubit is in 0 state, it will make it to be state 1. If the second qubit is in 1 state, it will make it to be in state 0, right? So these are very, very simple 2-qubit operations, but really important 2-qubit operations. So there was some question. Raunak Ranjan Mishra, he asks, have you discussed about the Blocksphere? Yes, we went through Blocksphere in the first few lectures, but I can send you slides if you write me an email, and I can point to some literature. It's very, very simple. No worries, no worries. I mean, we can also review it again some other time. But just drop me an email and I'll send you some necessary materials. No problem at all. Okay, so yeah, this was just theoretical calculations, right? And these are what we call ideal gates, right? Ideal gates. But we want to make quantum computer do those operations, and it is a non-trivial task. Companies are investing thousands and millions of dollars to build a very fast and very high fidelity, as we like to call them, very accurate 2-qubit gates, and to implement such operation in lab with real qubits, it's a difficult undertaking. And at IQM, we are building or have built fast 2-qubit gates, and this is IQM's my company's setup to perform 2-qubit gate operation. So in reality, our qubits, they look like that. So this is not just the IQM scheme. A lot of other companies and institutions, they rely on this sort of qubit architecture to build quantum computers. And MIT, they have also, there are also, of course, there are a lot of research papers on such kind of quantum computing architecture. And what we have here, we have 3 different qubits, right? So this is qubit 1, qubit 2, and this is the 3rd qubit, which we call coupler. And this is scanning electron microscope of chip, right? And quantum computer, you know, if the big one or the ones which you call universal fault tolerant will have millions of this sort of qubits lithographically laid out on a chip, and that is your quantum processor, right? But I'm showing you just a small chip, and this chip contains 3 qubits. That's a good question. What is the size? What is the feature of size? Yeah, that's a good question. I'm not exactly sure. nanometer. I think it's in millimeter. This whole chip should probably be in millimeter, if not micrometer. I would like to think. But these are not like atomic sized qubits, because these are electrical circuit, and these electrical circuits are made out of capacitors and inductors, right? So these are like macroscopic chunks, unlike ions and atoms, right? And so when we say qubits, they don't look like well-defined two-level system as you know, or as I have told you, but they are electrical circuits, and these are coupled, right? And we want to perform 2-qubit gate operation by interacting qubit 1 to qubit 2, right? So I told you that qubit 1 and qubit 2, they're just, you know, two-level system, right? 1 and 2, and these have state 0, 1. These have state 0, 1, right? And there are 4 computational basis sets, and you use those computational basis sets to perform C-phase gate operation. And these qubits also have well-defined energy states. 0, 1, 2 is slightly closer, 3 is even more close. We call them enharmonic oscillators. Again, these have well-defined energy levels. 3, 4, right? And this will be 0, this will be 1, this will be 0, this will be 1. Likewise, also the coupler has this energy levels, right? And you obtain this well-defined energy levels if you cool this superconducting circuit down to almost 0 Kelvin. And this big macroscopic circuits, they behave like two-level atoms. And we use states of this artificial two-level atoms to define our computational subsystems and perform the operations that you saw here, right? But it's a huge undertaking, as I told you. Building chip like this, it involves disciplines from chip fabrication technology to electronics engineer to, you know, people calibrating the gates, because you want to operate these gates with full accuracy, right? So it's not a small task. You need people who understand cooling devices, because you need cryogenics, you know, this fridge where you can cool the system to like almost 0 Kelvin. So it's a very non-trivial task, and people like a team, you know, 100 if not thousands of people, they work on this together to build something like that. And how you perform implementation of this 2-qubit gate on realistic superconducting circuit like this is you apply some pulses, right, on one of this qubit, and what happens is that, let me show you. What happens is that qubits, they get excited, they go to this other non-computational subsystem and comes back, and the phase of -1, right? So this, I'm talking about C-phase gate. Right. So this is a bit involved, and I'll not talk in more detail than that. But you have, for example, 2 qubits, right, coupled to each other. You apply pulse to one of this qubit, and you use 2 of their energy states to excite qubit and de-excite back. And in the process of excitation and de-excitation, it's going to pick up this phase of -1, right? And it gives you a desired C phase gate, right? So this is a bit involved, and I will go through it in more detail when you guys are a bit more mature with all these concepts. But in lab, that is how you do, right? So you are building first this chip, and these chips, they cool it down to 0 Kelvin. You have well-defined energy states such as this, and you apply pulse to one of the qubits, and you interact them, right? You interact those qubits, and it ultimately, after interaction for a certain time, it's going to give you C phase gate, right? And this is something we work on in our lab to implement what we call perfect C phase gate, right? With good fidelity, high fidelity C phase gate. Okay, you guys have any question about this? I didn't want to go too much into detail on the hardware implementation side, but what you guys should know is the definitions of this 2-qubit gates, and what each of these 2-qubit gate does to each of these 4 computational bases. Yeah. Any question at this point? So Ronak Ranjan Mishra to everyone, right? Is it always possible to obtain a deterministic outcome, regardless of whatever the state the qubit is in? No, it is not always possible to obtain a deterministic outcome. You can only obtain outcome in terms of probabilities. So if you have, for example, right, if you start your circuit, let me do it like this. So let's say you have your state as alpha 0 plus beta 1, right? And if you measure this, you will obtain state 0 with probability alpha square, and you will obtain state beta, sorry, state 1 with probability beta square, right? So it is always going to be probabilistic outcome. And for example, it's the same situation with 2-qubit gate. Your psi will be in state alpha 0 0 plus alpha 0 1 plus alpha 1 0 plus alpha 1 1, right? So when you measure, you are going to obtain this state with probability alpha 0 0 square, this state with probability alpha 0 1 square, so on and so forth, right? So it is always going to be deterministic, sorry, probabilistic. Okay, since we are running out of time, in the last few minutes, I will tell you what the project is going to be about. In this project, we're going to write quantum algorithm, which we call Grover's algorithm. And this is one of the simplest quantum algorithm, which people first discovered when they were thinking about quantum computers, right? So what does this algorithm do? So I think I mentioned to you something about phone book, right? And if you want to find your dad's phone number, right? And let's say it is unstructured. You don't have those keys, right? Or those labels A, B, C, D, and you need to query a lot, flip pages, sort of like trial and error, right? You flip page number 1, your dad's phone number is not there. Page number 2, your dad's phone number is not there. And you need to flip, like, if there are n pages, you need to flip n-1 pages, right, to reach at your dad's phone number. But if you use quantum computer, how many queries? We call this flipping of pages as queries. How many queries do you need until you get your dad's phone number, right? So this is exactly what we want to do in the project, and I'll formulate this in a nice PDF and send it to you guys. So you're asking, right, so which of these pages has your dad's phone number, right? And your dad's phone number is hidden behind this page, right? It could be here, it could be here, it could be here, it could be here, equally likely. And you flip the right page and you're like, oh, okay, finally it's there, the middle one, right? And in the worst case, it takes you to flip all these pages except for the last one to figure out, in the worst case, that's your dad's phone number. But quantum computer can do at a much faster pace. And we want to know with this project, how fast does quantum computer do this task, right? How many pages do you flip? And the result will probably surprise you, so this is why it's a fun project for you guys to look into. And I recommend solving or at least being engaged in this project. And we can talk more in the next lecture. But first, participate in this Discord channel, make a team, and I will email you guys the project, right, the PDF, early next week in the latest. And yeah, so now what we want to do is we want to go to our virtual cocktail. Let me send you guys the link. Copy link. All right, so let us meet here, guys, and we can talk more. Let me quickly take a screenshot of the list of participants today. All right, so I'll send you a link here. Let us meet in the virtual cocktail, guys. Thank you all for listening, and I hope you guys got a chance to learn something new today. See you.